So last video we stopped here. We define free body diagram, we define whatever things, and then we set up an equation. So now we're gonna simplify the equation, okay, so that we can actually have a certain conclusion to a certain stuff. Now currently we only have this relationship. We can't conclude anything, okay. So as just to recap, we clear all these things with summation of moment or maybe summation of whatever forces they have, and then we have an equation already. So now comes the very difficult part, is to find ways to simplify the equation and get our answers. Typically in terms of the frequency, I would say. Or in this case we are talking about the amplitude, okay, sorry. So we are trying to solve for the amplitude. So therefore, same thing, we're gonna solve using differential equation, the complementary and the trial function. So you give me a minute, I'll just write down everything. Okay, so this is the so-called how do I say, the complementary solution. Okay, so complementary solution includes the complementary function. I mean, this is the to solve for differential equation, we use the second order differential equation solver, which includes complementary function plus a particular integral. And then for complementary function is in this formula. One thing I want to make clear is that I just realized if you were to use this equation and then you were to find, because you remember there's three cases, case 1, case 2 and case 3. Typically this is case 3, but however we lack one of the e rho t multiplied to there. Okay, so we are lacking this thing. But however, we actually drop it out because I believe only lah. I don't know. I cannot confirm. Nobody confirm. Just that this is constant throughout. Okay, this is constant throughout because everything is dependent on the magnitude of the m and the k. So you can treat this as a constant. So it's just a one. So we just treat it as a constant one in order not to complicate the situation. So this is the only excuses I can find for myself. In order to you know, although it's not very strong, but I believe it's pretty much yeah. So after we set up the complementary function, it's just this. We have to find for particular integral, which is a little tedious. So maybe you give me a moment. Okay, so I've written down the particular integral. Okay, so we actually took the equation 1, which is this one, as we have defined earlier from equation 1. We just point over here, and then because particular integral wise, I believe, hold on, so for the particular integral, as I say, this is the you take equation 1, but if you remember, for particular integral, it's just if it's just one constant, you can just use this one, lambda. I mean some constant, other constants that is the same magnitude of this. Let's say if it's square, then you have to square plus a lower degree plus another lower degree. If you remember how the math works, okay? So it's just last time you have studied already. Just that in this case you will be wondering, if you understand what I mean, you'll be wondering that dude, why you want to take the whole equation rather than you just set this as a constant x and then you differentiate 2 times and then you just sub it inside and then you solve. One thing is that if you were to do that, you still get back the same, because you are not in terms of x. Okay, so this F itself is a friction force. This friction force is it cannot be described in terms of x, although it can be described, but it's a little complicated, or perhaps the approach that we are doing here is not in terms of that. So to solve for the particular integral, as you can see this type of equations, at the end of this section we will eventually get back a certain numbers, okay, which is in terms of there's no square or cube or no e, if you get what I mean. So apparently what we're gonna do is to actually eventually solve for this particular integral for this equation in terms of using a binomial theorem instead of the typical we sub in into there, because we cannot eventually differentiate this, and then make the things more complicated, I guess. So maybe you give me a minute, maybe I can do an example. Okay, so this is one example. If you were to, as I said earlier, if you were to get this f as some variable, if you were to say that f is equals to this thing, and then you differentiate 2 times, you get this equation which is very big, which is very weird also. And then we will sub it in back into this equation, and then back into this equation as, so this equation will become this stuff over here. Okay, and then m is here, and then k is k, and then x is just and because you didn't differentiate anything, so x1 is just this one, and then it's equals to f. So you want to solve for this whole equation, what the hell, right? Very tough, right? Another method is also if you were to differentiate 2 times, you just sub back in here, and then plus kf, and then equals to f, and then because friction itself is just a friction force, there's nothing in terms of time. Okay, there's in terms of, because you want to sub in your boundary condition in order to solve for this, but if you have no boundary condition, you cannot solve. So this is where the threshold point comes in, and people cannot solve it. So typically they will use binomial theorem. So they do not be confused of this thing. I'm not talking about this as a solution, but I'm talking about why you cannot use this method, the typical old method that we are using in math to solve for this type of particular integral. We can only solve this type of particular integral in terms of binomial theorem, so that we can derive a certain acceptable solution for the system. So give me a minute. Okay, so I have mentioned earlier the particular integral, we choose this equation first, and then we divide this equation by m. Okay, as per last time, we actually every time we do it, we try to make the second order thing into coefficient is equals to 1, meaning there is no coefficient, just 1. I mean, yeah, let's make it botak lah, okay? So there's nothing over here. So there will be like coefficient 1 times x. We don't want any coefficient other than 1, that's all. So we clear away all this, we just divide the whole equation by m, you get k over m, x1 equals to f over m. Yeah. So, and then after which we know that omega, the natural frequency square, is equals to k over n. And if you were to remember this equation, the natural frequency, so apparently this is just just to rewrite into this form, and then we can simplify this equation into this portion. And then the reason why you want to switch it to natural frequency is because typically we will want to, because when you're dealing with how do I say, you're dealing with graph and everything, it is best if you were to switch in terms of frequency or in terms of whatever parameters that is in the graph. So you have to remember the parameters are t and x. So if you were to make it in terms of x and t, that will be good. And then nonetheless, there will be a certain frequency in between the each wavelength or whatever, between the periods and everything. So this is why we change to the frequency itself, so it will be much easier to solve. And then for step 13, we rearrange the equation. We rearrange this equation using the binomial theorem, and where the binomial theorem is 1 plus xn. Okay, 1 plus x to the power of n is equals to a huge series of stuff. Okay, don't be intimidated by this. It's pretty easy to solve for that method. So apparently 1 plus xn, we're trying to make this equation, okay, into this form, such that we can solve using this series. Okay, hopefully you can get some thing out of it. So you give me a minute, I'll just continue. So 13.1, part of this chunk, this binomial theorem, is that we actually use the operator. Okay, if you don't know what is the operator, you just simply this is the basic definition. So the derivative of x is equals to dx, where the derivative d over dt is equals to d. Okay, so any power dn over dtn is equals to dn. So if it's the second differentiation, second order differential equation, d2 over dt square equals to d square. It will be equals to d square lah. So apparently what we actually are looking here is that we have um, there is 2 degree of differential equation, right? 2 degree of differential. It is a second order differential equation. Okay, so there will be a double 2 degree thing. Double dot. Okay, whatever. So it actually, if you were to sub in into this equation, it will be d2 dt square equals to d square. So this is how I get my d square over here. And another method is that you just straight away sub in x1 is equals to d, and then you differentiate 2 times in that particular manner. You'll get square. It's quite straightforward. If it's, you can take this as x d0. Okay. So yeah. So if it's d1, then so it'll be like 1. So you will like x1 or whatever. Okay, whatever. So you get approximately what the feel of it, and then you just sub in this dude over here in as a d square. So you are just getting d square plus omega n square x1. You so okay. I actually forget d square x1. Okay. So apparently this is why now this will be d square x1 plus omega n square x1. So you just factorize out the x1, you get this thing, and then similarly this is also f over m. There is a little slight mistakes. Yeah. So bringing this setup for the for later. So you give me a minute a while again. Okay. So after we explain the operator, then we have to rearrange. So we just bring this portion down here. Okay. So we just multiply everything by d square plus omega n square. So x1 is equals to fm times d square plus omega n square. And then we rearrange again. So this portion is a little more tedious, but rather it's quite easy, but troublesome enough. So we're trying to rearrange this equation into a binomial setup as like 1 plus x to the power of n. Okay, so you're trying to make this equation, okay, to make it in terms of this, so we can do a series of workings, and therefore as you can see, um, for this from here to here, we bring the f and the m out. So f over m times 1 over d square plus omega n square. But since you divide omega n square by, so for example, it's 1, then d square plus omega n square, right? Then if you were to divide this by omega n square, if you divide the whole thing by omega n square, you get this one. Okay, so this is what it means lah. You can try. So so this portion is just 1 over d square plus omega n square, that's all. And then uh, so and then you'll get this thing omega n square over here. So because you factorize out the omega n square. Okay, so apparently after which you bring this omega n square over here, so you become like that. And then you just flip this over in terms of d square omega n square plus minus 1 to the power of minus 1. So apparently as you can see, now we have the binomial theorem in this section over here. So it's 1 plus x to the power of n. Okay, so after which you can set up the binomial equation. which is 1 plus nx, since n is minus 1, so minus x, which is x in terms of this x is actually d square over omega n square, so we just minus d square over omega n square, and then plus whatever thing that is over here, you just do it out, and then you have a series, and then you multiply by, so this whole thing is just about a binomial theorem. So this piece is binomial theorem, and this piece is a multiple of this binomial theorem. Okay, so we have separated this whole equation into this manner, and then further simplifying it to binomial theorem. And then we can also simplify the simplify the m omega n squared in terms of k, because if you remember, the natural frequency goes to this thing. You bring this out, you become omega n squared, and then you bring the m out, you have k. So this is just a manipulation. Anyway, so after which you get this thing, and then you make assumptions. So assumptions wise, this assumption is a little ridiculous, but yeah. So assume k is very big. So you assume that we can either assume that k is very big, or we can assume, actually we cannot assume the k is very big. Never mind, you give me a minute. Okay, so either way, so I'm trying to explain why we choose omega as very big. So there is two scenario when we can assume that k is very big, so the movement of the x is very small. So what it means is that the stiffness of the spring is very big, such that when you pull it out, this mass over here, and then when you release it bounces kind of like, very little. And in this sense, it's not pretty much the case, because if your k is very big, eventually this whole thing will become 0, and then your whole equation will become, because whatever thing multiplied by 0 will be 0, and you cannot get your particular integral. So therefore, k cannot be as large as possible. So therefore, we will assume that m is very small. You may be very blurred why I'm talking about this. Is because if you remember, natural frequency is equals to square root k over m, right? So in order to make omega n to be big, okay, we're trying to make omega n to be big so that we can clear away all this stuff in order to have f over k, okay, as our final answer. So therefore, we would assume that either k is very big or m is very small. Okay, so we can assume that m is very small, it's very negligible. Therefore, we can make sure that k is very big. And therefore, this is why I have a side note over here saying that m is very small, so that we make sure that omega n squared can be assumed to be very big. And whatever divided by the very big number will becomes to 0. So d square over a very big number, infinity, will become 0 plus 0 plus 0, 0, 0, 0, and then therefore it's just 1 times f over k. Okay, so maybe I just, so thus whatever divided by m, so 1 times f over k is equals to f over k, and we have our particular integral as this. So just to summarize a little, and then I'll just end this video because I've talked quite a long time. So we derive our free body diagram, we derive this equation, and then we rearrange to have this equation over here, a non-homogeneous equation, and then after we derive the equation, yes, you can see we follow this steps, and then we finally get this equation, and then we have to find ways to simplify the equation, and this is why we have to solve the equation using differential equation method. So therefore we have a complementary function plus particular integral. Complementary function is simply this, and then now we're gonna solve a particular integral, which is kind of pretty much difficult. I've also explained why we solve in this manner, because there will be no solution if we solve using our last time we learned in math, that method. So therefore we do a long chunk of thing using binomial theorem, most probably the case, and then we eventually get this our particular integral. So at the end it will be like CF plus our particular integral. So that will be our general equation. And once we get the general equation, then we can start to solve for the particular equation. And then next video I'll just continue. So I will see you there.